Chapter 8, Functional Pipelines, Iterators, Streams, and Collectors. Chapter 8, Functional Pipelines, Iterators, Streams, and Collectors, is about processing data in Java with clarity and intent. Most backend systems spend a lot of time moving through collections, filtering records, transforming values, grouping results, validating inputs, and assembling output models. Java gives us several ways to do that, but the important choice is not whether a loop or a stream is more fashionable. The important choice is which style makes the data flow easiest to understand and safest to maintain. Iterators represent the traditional model. An iterator gives explicit control over traversal. You move through a sequence one element at a time, usually with has next and next. This style is still useful when control matters more than expression. If traversal depends on complex state, early exits, custom cursor movement, mutation through the iterator, or careful interaction with external systems, an explicit loop or iterator can be clearer than forcing the logic into a stream pipeline. Streams change the style. Instead of describing each step of traversal manually, we describe a pipeline of operations. A stream has a source, a sequence of intermediate operations, and a terminal operation. The source might be a collection, an array, a file, generated values, or an I/O-backed sequence. Intermediate operations such as filter, map, flat map, distinct, sorted, limit, and skip describe how the data should be transformed. A terminal operation such as collect, for each, reduce, count, any match, find first, or to list actually triggers execution. That lazy execution model is central. A stream pipeline does not usually run when the intermediate operations are declared. It runs when a terminal operation is invoked. This allows Java to combine operations efficiently and avoid unnecessary work in some cases. For example, if a pipeline filters a large collection and then uses find first, it may not need to inspect every element. The stream describes the data flow. The terminal operation determines when the flow is evaluated. The main benefit of streams is expressiveness. A well-written stream says what transformation is being performed. It can remove noisy loop variables, temporary collections, manual counters, and repeated conditional code. For simple and medium complex transformations, this often makes code easier to read. A pipeline that says, filter active orders, map them to customer IDs, remove duplicates, sort them, and collect the result, is close to the business intent. But streams can also be abused. A long chain of lambdas with nested conditionals, side effects, mutation, and unclear naming is not better than a loop. It is just harder to debug. A senior engineer should not use streams to prove cleverness. Use streams when the pipeline remains readable. If the code needs comments to explain every lambda, or if debugging requires mentally simulating too many steps, an explicit loop may be better. Collectors are where streams become especially useful for real backend work. A collector describes how stream elements should be accumulated into a result. Common collectors create lists, sets, maps, joined strings, grouped maps, partitions, counts, sums, averages, or custom aggregate structures. This is valuable because many business operations are not just transformations. They are aggregations. For example, a service might group transactions by account ID, count failed login attempts by user, partition invoices into paid and overdue, or build a map from product code to latest price. Collectors express those outcomes directly, grouping by, partitioning by, to map, counting, summarizing int, and joining are not just utility methods. They are vocabulary for common data processing shapes. The right collector matters. ToList is simple when you only need a list. ToSet removes duplicates. ToMap is powerful but requires care around duplicate keys. Grouping by is ideal when many elements belong under the same key. Partitioning by is useful when the classification is binary. Custom collectors exist, but they should be used carefully because they can be harder for teams to understand. Streams also encourage functional thinking, but that does not mean every Java codebase becomes purely functional. The practical rule is to prefer stateless, non-interfering operations. A stream pipeline should not usually mutate external variables, update shared collections, call unpredictable side effects, or depend on hidden state. Side effects make pipelines harder to reason about and can break badly if the stream is later made parallel. Parallel streams deserve special caution. They can split work across multiple threads and may help with CPU-bound operations over independent data, but they are not a general performance switch. They often hurt for small collections, I/O-bound work, database calls, HTTP calls, shared mutable state, or workloads where ordering and contention dominate. A parallel stream uses shared execution resources, and careless use can create unpredictable performance problems. In enterprise systems, streams are best used for in-memory transformations, not as a replacement for database queries. If the database can filter, sort, group, or aggregate efficiently, let the database do it. Pulling a huge dataset into memory and then streaming over it is often worse than writing the right query. Streams are excellent once the data is in the application and the transformation belongs in application logic. Readability is the senior concern. Good stream code uses meaningful method references, small helper methods, clear variable names, and short pipelines. It avoids deeply nested lambdas. It avoids hiding important business rules inside anonymous expressions. If a filter condition is important, naming it as a method can improve the code. Filter this is eligible for settlement often communicates more than a large inline predicate. There is also a testing angle. Functional pipelines are easier to test when the transformation logic is pure. If mapping, filtering, and grouping functions have no side effects, they can be tested directly and reused safely. If the pipeline mixes transformation with logging, database updates, remote calls, and mutation, the tests become harder and the design becomes less clean. The senior takeaway is that functional pipelines are about expressing intent. Iterators and loops give explicit control. Streams give declarative transformation. Collectors give expressive accumulation. None of them is universally best. A good Java engineer chooses the style that makes the operation clear, safe, and efficient. Use iterators when traversal control is the main problem. Use streams when transformation clarity is the main problem. Use collectors when the result is an aggregation or reshaping of data. Keep pipelines short, pure, and readable. Functional style should reduce complexity, not hide it.